1, 2, 3, 4.
Hey, good morning, everybody. It's Monday, so you know what that means. Monday morning review. This is when I assume you have completely forgotten everything that you learned in the last unit. Have you forgotten? No, of course not. You guys are machines, and I know that you remember all of this. However, what I thought I could do is spend a couple minutes doing a little bit of review today. Then I wanted to shift gears and start talking about PV diagrams. That's going to be sort of the central motif of the next week and a half, is how do we get useful work out of heat? Heat's a very disorganized thing, just like some of you. And what it does is, well, what we can do with heat is actually get it to do useful work. Again, just like some of you. So, no, I'm just kidding. Sorry, it's Monday morning. I'm feeling sarcastic. I think these notes might take 10 minutes. I want you to write them down as we go. And then I have an inspirational video for you to watch. It's got good music in the background. And it will actually outline what we've done this unit and where we're going. You might understand half of it, but by the end, you'll get it all. So, chapter 15. You ready? Take out a nice clean sheet of paper. No, really, take one out. If you just watch, you're not going to learn squat. You know that. I know that. Your mom knows that if she's listening. All right, you good? All right, so here we go. Chapter 13 and 14, which we just wrapped up, talked about gas laws. And the reason gas laws are so important is because it allows us to figure out what's going on in a gas. Right? Yeah, it's pretty easy. Now, what we are looking at is, let's say we have a closed system. I'm going to start at the top. In a closed system, which just means that we have molecules moving around with different velocities, there's a pressure caused by the collisions of those molecules with the container. There's a volume, as you can see, and the temperature is just a measurement of the average kinetic energy of the molecules. That has to be in Kelvin. Now, we can change the pressure in a system. Let's keep going. So in a closed system, I can say that P1 V1 over T1 equals P2 V2 over T2. Because of the work that Avogadro did back in the 1840s, we can also summarize that by using the ideal gas law. PV equals nRT, where pressure times volume is related to the number of moles times the ideal gas law constant times the temperature. Now here's the funny thing about the ideal gas law. Take a look at it, perv nerd. I don't know if you should say that to your professor next year, but that's what I call it, perv nerd. It's probably not appropriate. But if I take that formula and solve it up for P, that means divide both sides by V, right? I end up with PV equals nRT over V. Now let's just talk about that for a moment before we move on from that. Now, if I look at nR and T, so if P is equal to nRT over the volume, N is the number of moles of gas, R is the ideal gas law constant, and T is temperature. If T is constant, what's the word we use for something where the temperature doesn't change? Would that be isobaric? No, idiot. It'd be isothermal, right? If this is isothermal, N, R, and T are all the same at a given temperature. So I can say that the pressure is inversely proportional to the volume. Now, I went from equals to the alpha sign, the directly proportional, because the it's not equal anymore. There's still a constant involved. Now, if I were to graph that, pressure versus volume, what would that look like? Well, I remember as a student thinking, however, you guys know that this is just like if we graphed y proportional to 1 over x. And if pressure is my y-axis and volume is my x-axis, then my curve would look like that. Yeah? It's just that. Wait, which way am I? Nope. Oh, no. Yeah, like that. Okay. Now this is known as an isotherm. And for different temperatures, we would get different curves. Yeah. Just let that sink in for a little bit. Isotherms. Okay. Now, other things from the gas laws and heat unit. We could find the internal energy of a gas, 3/2 PV. That's for a monatomic gas, although there are times when maybe it's used with oxygen, but it really should be used for a monatomic gas. Internal energy of a gas could also be 3/2 nRT or 3/2 big N KT. And if you remember, we were able to find the velocity root mean squared, where I see that the velocity is proportional to the square root of the temperature and the mass times 3 constants, right? Okay, so that was gas laws. Boom. Next, heat is transfer of energy due to a difference in temperature. Check. Now, we looked at the mechanical equivalent of heat, we looked at the electrical equivalent of heat, and how it all tied together in something we've been using since early last year, the law of conservation of energy. Now, there's another way we could state the law of conservation of energy, and that's known as the first law of thermodynamics, which sounds way scarier than it is. In fact, it's actually easy. It's just addition. You can handle that. So, you ready? Write this down. The first law of thermodynamics. Then give yourself a drum roll. There it is. Delta U is equal to Q plus W, where delta U stands for the change in internal energy of the gas, Q is the heat added to the gas, and W is the work done on the gas. Okay? Work done on the gas. Now, I have to tell you that the sign in our textbook is different. They use a negative sign. Relax. This is the way we should treat it. Okay? So if you read ahead, the signs are different in the textbook. It's okay. You got this. So delta U equals Q plus W. What does that mean? Well, to change the internal energy of a gas, if I add heat to it, if I add heat to a gas, what would happen to the internal energy? Well, yeah, it will go up. What if I do work on a gas? Now, how do I do work to something? I can do work by pushing against it. Right? If I push against something, I do work. I apply a force over a distance. What happens if I do work to a gas? What does that look like? That looks like compressing that. So I can do work by compressing a gas. How can a gas do work on something? Well, it would be the opposite. It would push against, right? That's not that hard. So heat is when you add heat to a system, you can increase the internal energy. If you do work on a gas by compressing it, you would also increase the internal energy of the gas. Okay, there it is. Now this entire unit, the next week, here's what I need you to picture. Everything we're doing is connected to this. Now, are you going to really understand what this picture is right this second? Nope. That's okay. It's foreshadowing, kind of like you've already seen this formula before. But here it is. I'm going to put a gas in a cylinder. And if I add heat, which we use the symbol triangle, if I add heat to that gas, what's going to happen to the molecules? They're going to move faster, right? They're going to apply more pressure to the cylinder. And if it's free to have the volume change, it's going to expand, move to the right. As it does that, it can apply a force over a distance, and the gas can do work. That can turn a crankshaft, which can turn a flywheel, and connected to that flywheel could be a belt, which turns everything else. That's it. That's a heat engine. That is what a good portion of our society is based on. A cylinder with gas in it, you add heat to, turns the crankshaft, makes a flywheel move. That's it. Yeah, I wish it were that simple. Now, that visual I knew was going to be difficult for you. So I found this image. Maybe we'll talk through it. So here we're looking at a 4-piston engine. And what I see is I've got gas. Oops, I can't draw on this. Let it soak in for me. Put a gas between the blue and the gray. Ready? It compresses. I'm looking at the bottom one here. Compresses, add heat to the system, and it pushes away. Compresses, pushes away, and does work. Compresses, pushes away, and does work. If I connect that to something else, say a flywheel. Now, a flywheel, it's called that. It's going to have a lot of mass. It has a lot of rotational inertia. And once it gets spinning, it keeps on spinning. Now, what if I put a blade on the other end of that shaft? A big one, about 22 inches wide. And then I walked back and forth on my grass. What would happen to that grass? That's right. I'd have a lawnmower. I just think you guys need a visual of a piston moving back and forth. Pistons move back and forth. That's what they do. We then have mechanical systems that convert that back and forth motion into rotational motion. And from there, we can do anything. That's the point. All right. So from a physics standpoint, we are going to look at how the change in internal energy of a gas does work. Now, I can get that to happen in a number of different ways. Are you guys good? So, in your notes, you probably didn't draw a picture of that flywheel setup. That's okay. But so far, we've done a review of a review of gas laws and heat. I have now introduced the first law of thermodynamics, and next we're going to move on to graphs. Now, if we look at a sample of gas, go ahead. Actually, you know what? I'm going to be quiet for a moment. Actually, you're going to push pause. Push pause. And draw this. Wait, no. Draw a picture of this and push pause. Okay, good. Now that you've drawn this picture, here's the deal. What we're going to be able to do is not just add heat to the gas. Because if we did that, it would just expand and it would only go in one direction and it wouldn't be repeatable. The thing about a thermodynamic process, the thing about an engine where we turn heat into work is you can't do it just once. If you do it once, it's an awful lot of setup, right? For the piston to expand one time. You need it to happen over and over and over and over and over again. So let's look at this graph. If the internal energy of a gas, U, if I add heat, it could actually do 3 different things. It could change the pressure, it could change the volume, or it could change the temperature. When you first learn about this stuff in chemistry, or back when we did gas laws, we tried to keep things simple. If you think back to our P1 V1 over T1 equals P2 V2 over T2, it seemed like we always kept one of those constant, like we kept the temperature constant. And if you double the pressure, what happens to the volume? You know, that kind of thing. But what if it's not always the case? Well, if I look at my P versus V, or my PV diagram, as I showed you before, the pressure is inversely related to the volume at a given temperature. So because of that, we end up with these isotherms that look like those 1 over X graphs. Yeah. Okay. Now, the less the temperature is, the lower the temperature is, the lower the isotherm curve would be. So I just drew in 3 different sample isotherms. One that is low temperature, one that's medium temperature, and one that's high temperature. Hence the TL and the TH. Now, when we look at different processes in thermodynamics, there's 4 of them that you need to know the names of and what they represent. Write this down. In an isobaric process, there's no change in pressure. Iso means no change, so you figure out what the next word. Isobaric means the change in pressure is 0. Isometric, change in volume is 0. Isothermal, duh. And here's the last one, which I know you haven't heard this word before. Adiabatic. Talk about it tomorrow in more detail, but adiabatic is when the heat is 0. There's no heat exchange because it happens so fast. Those are quick processes. Now, how does this all tie together? Well, last picture, and then we'll call it. Actually, I might check my time and see if I'm just not too much on here. That's a nice visual, isn't it? Really stare at it. All right, so in the last 3 minutes here, I just want to go with what happens in different processes. Okay, and here's what I need you to draw right now. Again, you might have to push pause. Oh, I can't erase that for this diagram. Now, are you ready? I think I may draw it with you. P, V. Now we measure pressure in pascals, which is a Newton per meter squared. Volume we measure in meter cubed. And here we have our isotherms. Temperature low, temperature high. And I'm going to start off at a position. We'll call this position A. Yep. Okay, now you're caught up. Ready? If I were to take this gas through a thermodynamic process where the first step was I allowed the gas to expand while staying at the same pressure, I am going to call that process AB. And what would I call that? I would call that isobaric expansion. Isobaric because the pressure didn't change, and expansion because the volume did. Because the key to understanding this whole unit is every time you see one of these graphs here, what I need you to visualize is a piston underneath, where at A, it was down here full of gas. But now at B, it expanded, the gas is expanded in the piston like this. Boom, AB. Okay, next process is going to be isothermal expansion. B to C. Now, Josh, I know at this point you're going to start asking, like, how do we apply this? We're not there yet. I know you're thinking, though. That's good. It's good thinking, but not quite yet. All right, so isothermal expansion. Next, what if it drops down to a lower temperature, and in CD, that's going to be isometric expansion or contraction? Neither. Nice, guys. Good. Because the volume stays the same. It's just isometric. But because the pressure went down, the temperature also had to decrease. Okay. And then the last one, process from D to A. Whoop. And I blew it. Timeout. Timeout. This is where I would edit the video if possible. Is right here, C to D. Okay. Now, fortunately, you guys all have nice pencils with erasers. Fixed. Okay. From C to D, we are going to have adiabatic compression. Or, I'm sorry. I can't believe I have to do these all in one take. Adiabatic compression. I will explain that all tomorrow. All right, everybody. So I've got a quick demonstration of adiabatic compression. Mr. Croto is unavailable, so instead I got a better student. Hannah Edgar is going to step in his place today. What I have here is something called a fire piston, and it's got an O-ring on the end, so it forms a nice seal. Oh, that's right in front of your face here. I've got a tube here that's hollow, a piston, and on this block I've taken a match, cut the head off, and I placed it right there. Now in adiabatic compression, the key is it happens so fast that heat does not have an opportunity to flow out. And if heat doesn't flow out, Hannah, what's going to happen to the temperature?
It's going to increase.
That's right. And if that increases, then the internal energy of the gas is going to increase as well. So if we're able to do this fast enough and compress that gas down into a much smaller volume and not allow any time for heat to flow, the temperature has to increase. And if the temperature increases dramatically, we should be able to spark that match. Got it? All right. This is a 50-50 deal. We'll see how it goes. So I'm going to depress the top of the piston very rapidly, and we'll see if we can get a spark. Hannah, you good? You're going to be our witness. All right. So, ready? Here we go, Hannah. You ready? All right. What do we call this? Adiabatic compression. Ready? Set. Oh, we had it. We had it. Oh, that counts. That counts. Adiabatic compression. The heat did not have a chance to flow. All right, you guys, so today's lesson is going to be on adiabatic expansion. And unfortunately, you can't be here, but you know who can be? Mr. Croto. There he is. Mr. Croto. Right, Mr. Croto right there. He's going to stand in for Sam today. And you'll notice he's apparently barefoot in school, and he's got the cinch going on as well. Adiabatic expansion. Best example I can come up with for adiabatic expansion is what happens with a fire extinguisher. Now, this is a carbon dioxide fire extinguisher under pressure. Oh, wait, it's down here. It's under pressure. So as it expands rapidly, what will happen is heat will not be able to flow into the gas in order to increase its temperature. So you know what's going to happen? There's going to be a drop in temperature, a dramatic drop in temperature, because no heat is allowed to flow. So this is called adiabatic expansion. The only thing Croto's going to do is tell us if it's hot or cold. You got it? Are you ready?
No.
So now I'm going to shoot it. Oh wait, no, I'm not going to shoot it at his head.
That would be dangerous.
Oh my God, that would be funny.
Yeah.
All right, next time. Here we go. Ready?
Ooh, that's cold.
It also happens to be empty, which I did not realize when we came into the building.
It was still cold.
Was it?
Yeah.
Cut. Well, that didn't work.